Example 2. Here I am going to discuss a reducible Markov chain. Here also we have only two states. The probability of system is moving from state 0 to 0 in the next step, the probability is 1, and the system is coming from the state 1 to 0 in one step, that probability is 1. So, this is a state transition diagram of a time homogeneous discrete time Markov chain. So, I am going to write what is the one step transition probability matrix for this state transition diagram or for this discrete time Markov chain. So, 0 to 0 one step, that probability is 1, 0 to 1 is 0, 1 to 0 is 1 to 0 is 1, 1 to 1 is 0. You can verify whether this is going to be a stochastic matrix, because each elements are lies between 0 to 1 and the row sum is 1, therefore, this is a stochastic matrix. So, both are equivalent, the state transition diagram and the one step transition probability matrix is one and the same. Now, we will try to find out what is the classification of the states. Go for the state 0, the P 0 0 of 1, that is 1, that is one step transition of system is moving from the state 0 to 0, that is going to be 1. This implies the state 0 is a absorbing state. Now, we will try to find out what is the classification of the state 1. So, if you find out f 1 1 of 1, what is the probability that the system will come to the state 1, given that it was in the state 1 and the first time visit to the state 1 exactly in the first step. So, that is going to be not possible, because with the probability 1 it moved to the state 0, therefore, this is going to be 0. And if you find out f 1 1 of all the subsequent steps also, that is also going to be 0, because if the system start from the state 1, in the next step itself it goes to the state 0 with the probability 1 and it is not coming back. Therefore, now we try to find out what is a capital F 1 1, that is nothing but the summation of all the Fi's, summation of all the Fi's, and that is going to be 0. If you recall the way we classify the state is going to be a recurrent or transient, we said f I a is going to be 1 or f I a is going to be less than 1. So, that less than 1 includes f I a is equal to 0. So, basically our interest is to classify whether with the proper distribution the system is coming back to the same state with the probability 1, that is f I a is equal to 1, and all other things we say that is a transient state, it includes f I a equal to 0. So, here with the probability 0 the system is not coming back to the state 1 if the system start from the state 1. This is always a conditional probability, and this conditional probability f 1 1 is equal to 0 implies the state 1 is going to be a transient state. So, whenever for any state I, f I a is equal to 1, that concludes the state is going to be a recurrent state, and whenever the f I a is lies between including 0 excluding 1, that is less than 1, then that state is going to be called as a transient state. Since since you have only two states, that is a state space is 0 and 1, and you will end up having a one observing state and one transient state. Therefore, the state space is partitioned into one closed communicating class which has only one element, and the transient state is 1. Therefore, I can say the state space S is a partition into closed communicating class C1 which consists of only one element, and the collection of all the transient states, that is only one element. So, this is a notation for capital T collecting all the transient states in the state space in the DTMC, and C1 is the first closed communicating class and which has only one element. If any closed communicating class has only one element, then it is going to be called it as observing state. Therefore, 0 is the observing state and 1 is the transient state. Since you have a C1 union T becomes a state space S, therefore, this Markov chain is not a irreducible Markov chain. Therefore, this is called a reducible Markov chain. This Markov, whereas the previous example is a irreducible Markov chain. There we have two elements and both the elements form only one closed communicating class, whereas here you have one closed communicating class with one element and the transient state is 1. Therefore, it is going to be a reducible Markov chain. There can be more than one transient state. Now, I am moving into the third example, so that I am explaining some more concepts through the examples. Example 3. Here I will go for 4 states which consist of states 0, 1, 2 and 3. It is easy to explain through the state transition diagram than the one step transition probability matrix. So, I am just drawing the state transition diagram for this DTMC. So, 0 to 0 one step, that probability is 1/3 and 0 to 1 is a 2/3. Therefore, row sum is taken care, that probability summation of probability is 1. Now, I am going for the state 1. State 1 to 0, that probability is 1, therefore, that row is taken care. Now, I am moving to the state 2. State 2, the self loop has the probability of, and going from the state 2 to 0, that probability is off. Therefore, this row is also taken care. Now, I am moving to the state 3. State 3, it has the self loop with the probability of, and it has the moving from the state 3 to 2, that probability is off. My interest is to classify the states for this Markov chain. Markov chain has 4 states 0, 1, 2 and 3, that is a state space capital S. Now, we will start with the state 0. So, you find out what is F00 of 1. In one step, as a first visit, the system has to come back to the same state 0. So, that probability is 1/3. You find out F00 of 2. F00 of 2, exactly 2 steps, as a first visit you have to come back to the state 0. That means, you can go to the state 1 by starting from the state 0 and come back to the state 0 in the next step. Therefore, it is a 2/3 into 1, therefore, it is going to be 2/3. Then you go for what is the possibility. I will take 3 steps, exactly 3 steps coming to the state 0. As a first visit, it is not possible, whereas the P00 of 3 is possible. F00 of 3 is not possible, because in 3 steps you cannot make a first visit. Therefore, that is going to be 0, not only F00 of 3, and for all other things also it is going to be 0. F00 of n equal to 0 for n is greater than or equal to 3. So, now I can find out what is capital F00. If I find out capital F00, I have to add all the values. So, it is 1/3 plus 2/3 plus all the further terms are 0, therefore, it is going to be 1. Since f00 is equal to 1, you can conclude the state space 0 is the state 0 is going to be the recurrent state. The similar exercise you can do it for the state 1 the same way. You can conclude f11 is also going to be 1. The other way, since the state 1 is communicating with the state 0, since the state 1 is communicating with the state 0, therefore, this is also going to be of the same type. Therefore, the state 1 is also going to be the recurrent state. Now, we can go to the state 2. So, the state zero comma 1, that is going to be the recurrent state. Now, I will move it to the state 2. So, whereas the state 2, if you find out f0, f2, 2 of 1 in one step coming back to the same state, that is going to be of f2, 2 of 2 steps, exactly 2 steps, that is not possible, that is going to be 0 and so on. Not only 2, and all the further steps also going to be 0, because with the probability of it takes only one step come back, and all the further steps it takes with the probability of it is not coming back at all. Therefore, this is going to be for greater than or equal to 2, it is going to be 0. Therefore, if you compute f22, capital F22, then that is going to be off plus 0 and so on. Therefore, you will end up off which is less than 1. Therefore, you can conclude the state 2 is going to be transient state. Not only the state 2, if you do the similar exercise for the state 3, the same thing, you may land up f33 is also going to be less than 1, whatever be the number. You can conclude the state 3, that is also going to be the transient state. You can find out the periodicity for the recurrent state only, not for the transient state. Therefore, now we can try to find out what is the periodicity for the state 0 and 1. Before that, we will try to find out what is the type of recurrent state, whether it is going to be a positive recurrent or null recurrent. If you find out mu 0 0, mu 0 0, that is nothing but 1 times 1/3, 2 times 2/3, 3 times 0, 4 times 0 and so on. So, if you sum it up everything, you may land up 1 times 1/3 plus 2 times 2/3, that is going to be 1/3 plus 2 times 2/3. So, that is going to be 3, 1 plus 4, that is 5. So, which is a finite quantity. You can conclude the state 0 is going to be a positive recurrent. Similarly, if you calculate f mu 1 also, you may land up with the finite quantity. So, you can conclude both the states are going to be a positive recurrent states. Here the state space is classified into 2 positive recurrent state and 2 transient state. Therefore, this Markov chain is going to be a reducible Markov chain, in short form MC. It is a reducible Markov chain because the whole state space capital S is partitioned into one closed communicating class which consists of the state 0 and 1 and the transient states 2 and 3. Therefore, this is going to be a reducible Markov chain. You can find out the periodicity of these 2 recurrent state also. So, if you find out D0, that is going to be greatest common divisor of what are all the steps in which the system will be come back if the system start from the state 0. So, either it can come back with the one step or either it can come back with the 2 steps, or it can make a one loop here, then one loop, then here. Therefore, it can come back from the 3 steps and 4 steps and so on. It need not be the first visit. Therefore, the GCD of 1 step or 2 steps and 3 steps and so on. Therefore, this is going to be 1. That means it is a aperiodic state. Therefore, whatever we have done it for the state 0, you can do it for the state 1 also. So, that is also going to be 1. The period is going to be 1. Therefore, both the states 0 and 1 are the positive recurrent and aperiodic states, and other 2 are going to be the transient states. Since this state 0 and 1 are going to be positive recurrent as well as aperiodic, and these 2 states are ergodic states also. Later we are going to explain ergodicity, the property. For that property you need to understand what is ergodic state. So, whenever the Markov chain has a few states going to be a positive recurrent and aperiodic, then those states are going to be called it as a ergodic states. So, later I am going to give the definition of ergodicity and so on.